Hello and welcome to our Signals and Systems mini project. We are students of Sardar Patel Institute of Technology and our branch is Electronics and Telecommunication. We have conducted this project under the brilliant guidance of Dr. Majid Katte and Dr. Shanti Swami. I am Sagar Bedi and my fellow group members are Kushal Deshmukh and Chinmay Deshmukh. So the topic of the mini project is application of convolution in image processing. As a preview of this, you can see how the image of the cute smiling dog was blurred. Now we achieved this using convolution. How? More on that later. So as an introduction to our mini project, it's based on image processing using convolution. Like I said, we got interested in this topic because well, one of us saw a video that the YouTube creator Three Blue One Brown uploaded. We also had convolution in our subject theory in our class, and so our interest was piqued by it, especially the part about how you can play with images using convolution. Now, you may be wondering, how can you play with images using something so abstract as convolution? Well, I'm here to tell you it's not at all abstract, and so we also based on project on it. So, what is convolution? Convolution is a mathematical operation used to combine two functions to produce a third function that represents how one function modifies or interacts with the other. That look feels like a big mouthful. You may not even have understood that. So, in simple words, imagine convolution as sliding one function or a filter, say, over another function or any data that you have to measure the overlap between them at each point. This is widely used in many fields like signal processing, image processing, physics, and even the new machine learning. Now, I would like to invite my friend Kushal Deshmukh to proceed with the presentation. I'll pass the baton on to him.
So let's now see how convolution works in image processing. So convolution is a mathematical operation to analyze, transform, and extract information from visual data. It involves application of filter, or it may also called as kernel, which helps for detection of patterns, enhancement of features, and removal of noise. By systematically combining pixel values with kernel, convolution helps process and interpret complex image data. In image processing, convolution is used for a variety of tasks, such as edge detection, blurring, and sharpening. Let's now move on and let's see how image processing can be done with the help of the software Julia. So Julia is one of the best software for image processing tasks and also for high data intensive tasks such as machine learning and simulation. One of the major advantages of Julia is its ability to seamlessly handle complex mathematical operation with ease. It also has wide range of libraries and frameworks such as images.jl and image filtering.jl for image processing tasks. Moreover, Julia also integrates well with other languages such as Python, C++, and MATLAB, giving users a vast array of existing libraries and tools while still benefiting from Julia's performance.
So, anyway, image blurring using convolution. So, here we have the popular video game character Mario. Now, I'll show you how you can blur this image using convolution. So, it's simple really. You just what is an image? It's just a collection of pixels, right? And each pixel has either a R or a G or a B, that is a red, green, or blue. So what you can do to blur it is you can translate that pixel into the blurred image by also including the pixels around it in a specific weight. Like you can see here, the matrix that we are using for the convolution is a 3 by 3 matrix and each square has a 1/9 weightage. So basically what we are doing is, suppose we are using the pixel that we have illustrated in the right bottom image. Suppose so anywhere we have to The pixel that we're blurring is the center one. So in that matrix, the center one is red. So 1/9 of it is red. The other ones that are red also get multiplied and added to it in a 1/9 weightage. The black ones, similar process is followed for the black and the gray ones. So what this does is it allows the neighboring pixels to sort of merge with or influence the center pixel, and this results in a slightly dimmed or blurred pixel image. So the red pixel won't be red, truly red anymore. It will be a sort of mixture of red, black, and gray, depending on the pixels around it. So what we can also use here is like a Gaussian kernel. Now, what is a Gaussian kernel? It's exactly what it sounds like. A Gauss function is something that gives you a bell curve. Now, why would we use Gaussian kernel here? Because the bell curve is also similar to how light actually refracts in real life or scatters in real life. So that closely resembles to the actual uh, occurrence of light, the shape of the bell curve. What we do in the Gaussian kernel, we give more weightage to the central pixel, and as we keep going out from the central pixel, the weightage drops. What this does is this gives you a smoother or a sharper blur, because it's while it's still getting blurred by the neighboring pixels, it still retains much more of its original color than otherwise. Also, another advantage of a Gaussian kernel is that in the frequency domain, it just acts like a low pass filter. So it just basically stops all high frequency noises, or at least reduces it a lot. I would now ask my friend Chinmay Deshpande to continue.
So, as my friend Sagar has explained beautifully the concept of image blurring using convolution, so now I would be showing you how we implemented this in Julia language. So here you can see this is called a Pluto notebook. This is similar to a Jupyter notebook where we use the Python programming language, but here we would be using Julia because as my group member Kushal had explained, it has wide ranges of functions and libraries for the application of DSP or digital signal processing in this context. So here we start by importing some useful libraries: statistics, images, FFTW, this is for fast Fourier transform, DSP, digital signal processing, and this is the most important one, image filtering, and we would be using functions which are included in this library. So as my friend Sagar had explained, we would be using a Gaussian kernel. Uh, Now, I would like to attract your attention to this. This is a visual representation of the Gaussian kernel, and I have taken a standard deviation of 4. So this looks quite big. If I use standard deviation, which is less, and run it, you can see it has become a lot less smooth. So we would be seeing how this affects the blurring. This would basically mean the blurring would be less, and if I increase the standard deviation, the blurring would be more. I have also written a function called shrink image in case we have an image which is quite big, and it has two parameters, image and ratio. The ratio is used to scale the image down. Now I have loaded a picture of a dog here, which we are going to blur using the Gaussian kernel. You can see the size is not too much, so I have not shrunk it. Now we come to the main meat of the project, the convolve function, which is used to convolve this image. Let me first show you what it actually does. This just blurs the image very beautifully because of the kernel which we have used. So here, let us see how these functions work. This is the convolve function which takes two parameters, the image and the kernel. And we can also see this is basically used to, this is a clamp function, which is a helper function that ensures if the convolution kernel tries to access pixels outside the image boundaries, it just gets clamped to the closest boundary pixel. In this function we can see this clamps the row indexes, and this clamps the column indexes. Then we can now we can see how the convolve function works. So first we extract the height, the width, then we divide it by 2, and this is where we would be storing our new image. So for every pixel ij, we calculate the weighted sum of the kernel applied to the neighboring pixels for each color channel. For why each color channel, I would explain it a little later. But the weighted sum concept is based on the Gaussian kernel explanation which Sagar gave. So here we are going into the nested loop. Here we process each channel separately. What this does is it iterates over all pixels in the neighborhood defined by the kernel. It multiplies each kernel weight. This is the kernel weight, and it multiplies it with the corresponding red channel value. This is the red channel value. This and this sum is used to sum up all the weighted contributions for the red channel. This function is for the red channel, and similarly for the blue, and similarly for the green. This clamp 0.01.0, this just ensures the resultant pixel intensity remains within the valid range, because this is just how I've written the function for better visualization. So here we can see a beautiful convolved image, blurred image of a cute dog. So now we would see another application, image sharpening using convolution. So you might be wondering, how can we sharpen an image? I would show you how we can do this in Julia Notebook. We would basically need to change the kernel. So as we can see, this is the new kernel which would be using. It has so I don't think so I explained how I've written the show colored kernel function. This basically what this does is if the value in the matrix is negative, it gives it a red color, and if it's positive, it gives it a green color. And this is used to adjust the intensity. If it is more positive, then it would be more green, and if it is more negative, then it would be more red, and vice versa. So this is the kernel we would be using. And what this does is, if this is the dog image, it would cause it to sharpen. It's interesting, right? Another application would be, this is quite interesting, edge detection using Sobel filters. Here we would be using this kind of a filter where positive values would be concentrated on the left side of the kernel, and negative values will be concentrated on the right side. So you might ask, why would we use this kind of kernel, and how do we get this interesting pattern of pi character from this? What this actually does is, if we are present in this area, suppose, where all the pixels are of the same weight or same color, this would not give any value, because the the sum here we can see it is 1. And if we multiply all the same colors with this, basically if we multiply 1 with itself and then subtract all the values, we would get 0. So we are not detecting anything here. And if we see here this white area, and if we if I would say that these two columns are present in a brighter area and this column is present in a darker area, that would mean the contribution of positive part is more and the negative part is less, which we can see here. The blue region, here we can see the brighter contribution is more, and which is why we get a blue representation in the pi model. But if we are present here, suppose there is it is more dark on this side, suppose these two are more darker and this is present in the brighter side, so we would have more contribution of the negative side, which would lead to negative red color being displayed, which I have represented in my function. So now I would like to show you how edge detection works. This is basically a vertical edge detection. This detects the vertical edges, and similarly if we change the kernel like this to a horizontal type of thing, we can detect the horizontal edges. Now let's see how we can implement this in Julia notebook. I would be loading a Mario image here to show you how this works. I'm changing the kernel to the a different kernel, which is basically a Sobel. It is called a Sobel filter, and this is an inbuilt function in Julia, which is why I like Julia. We have a variety of functions which we can use for the signal processing domain. So you can see this is the pixel which I have derived from the function I wrote. This is same as what I showed in the PPT here. Now let's see what it does. So here you can see how it detects only the vertical edges. And if I change the filter here to the horizontal filter, you can see how it detects the horizontal edges. Really fascinating, right? So now I would like to call my friends again and say thank you to all our viewers for watching this video.